We can make it live now. We can. It is 1 minute. It is. You can make it live. Yeah.
I'm ready.
Yeah. So you can just confirm when it is live. Actually, I will just introduce. Okay, it is live now.
Yes, it is.
Okay. Thank you. Thank you. So. So good evening. Good evening to all the esteemed members of the Ocean Society of India, ladies and gentlemen. As you are aware, the Ocean Society of India conducts the invited talks as a part of the OSI webinar series that is held once in every month. And this talk is arranged from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, and allied disciplines. This webinar series is mainly targeted for students, researchers, scientists, engineers, and working professionals in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, with a motive to impart and improve the knowledge benefiting the OSI community. I request all the members to actively participate and get involved in all the lectures under the OSI webinar series that is held every month. On behalf of the Ocean Society of India, it is my proud privilege to welcome today Dr. Supriyo Chakraborty, visiting faculty at the Department of Atmospheric and Space Sciences, Savitribai Phule Pune University, Pune, for this invited talk today. Dr. Supriyo Chakraborty will be delivering a talk on the topic application of precipitation isotopes in studying the monsoon processes, a topic that is highly relevant today in context to water resources and agriculture sector. Dr. Supriyo Chakraborty completed his bachelor's honors degree in geological science from the Indian Institute of Technology, Kharagpur during 1984, and master's MSc in exploration geophysics from IIT Kharagpur during 1986. He completed his PhD on paleoclimate from the MS University of Baroda, Gujarat during 1993. He worked as Scientist D at Indian Institute of Tropical Meteorology, Pune during 2007 to 2013, wherein he established the state-of-art paleoclimatology laboratory and built eddy covariance-based observational program in the forest ecosystems of India. His study demonstrated that for the first time that Kaziranga forest in Assam may be acting as a net source of carbon in the atmosphere. From 2013 to 2018, he worked as Scientist E at Indian Institute of Tropical Meteorology, Pune, wherein he coordinated the precipitation isotope analysis project in India. His novel contributions demonstrated that the corals from the equatorial Pacific Ocean and the southeastern portion of the Arabian Sea has potential to quantify the past monsoon rainfall over India. Several studies were performed demonstrating that the water isotopes can be used to study the monsoon processes for delineating active and break phases of the monsoon. Also, it can be used to estimate the monsoon withdrawal date. From 2018 to 2022, he worked as Scientist F at IITM Pune and as Project Director of the MetFlux India project, wherein he played a very crucial role in carbon sequestration studies for the forest ecosystems of India. Dr. Supriyo Chakraborty started his initial research career in paleoclimatology and paleoceanographic studies, Subsequently, he diversified the domain of research into atmospheric and climate science. His research interest includes the paleoclimatic reconstruction, especially the monsoons using natural archives. He also worked on the isotopic analysis of precipitation to study the moisture dynamical processes and used eddy covariance technique to quantify the atmosphere biosphere, carbon exchange, and energy fluxes in the natural ecosystems. He is also actively involved in the study of greenhouse gases in the urban environment. Dr. Supriyo Chakraborty has guided 3 PhDs and 1 ongoing. 5 students have completed their MSc dissertation under his guidance, and presently 1 is ongoing. In addition, 16 students have completed their summer internship program, and 1 is ongoing. He is very actively involved in teaching climate science to the students of Savitribai Phule Pune University and the University of Hyderabad. His teaching contributions are also involved institutions like the India Meteorological Department, ISER Pune, and the research scholars of IITM Pune. He conducted several training programs on greenhouse gases and the eddy covariance technique at IITM Pune, and also played a crucial role as the course director of the SERC School on Global Warming and Climate Change at IITM Pune during December 2010. Dr. Supriyo Chakraborty has published about 90 peer-reviewed research papers. He is a recipient of the Certificate of Merit Award by the Ministry of Earth Sciences, Govt of India. He is coordinating lead author and an editor of the book, Assessment of Climate Change over the Indian Region, a report of the Ministry of Earth Sciences, Govt of India, that was published in 2020 by Springer, Singapore. So with this brief introduction, it is my proud privilege to kindly invite our speaker, Dr. Supriyo Chakraborty, to deliver the talk. The participants are requested that the questions and answers session will be attended after completing the talk, and the questions can be messaged for the speaker in the chat box. So may I request Dr. Supriyo Chakraborty to please start the talk.
Yes. Good afternoon, everybody, and thank you, Dr. Prasad Bhaskaran, to give an introduction about myself. Now I would like to start my presentation. Is it visible now?
Yes, it is visible.
Okay. The title of my talk is Application of Precipitation Isotopes in Studying the Monsoon Processes. The Arabian Sea and Bay of Bengal, as we know, that they produce huge amount of moisture, and which is transported to the Indian mainland, and which causes monsoon precipitation. And there are several methods to study the monsoon, the dynamical transport system of the moistures. However, we like to use a somewhat different technique, that is precipitation analysis, isotopic analysis of precipitations. So in this talk, I will discuss in detail what we have been measuring the precipitation isotopes in an island in Bay of Bengal, that is Andaman Island. Just to give a brief introduction about the processes, for example, we know that though the Arabian Sea and Bay of Bengal, they have similar latitudinal range, however, their physical processes differ significantly. For example, the precipitation in case of Arabian Sea, the precipitation is less and evaporation is more. I'm sorry that this P greater than E, actually it should be for the Bay of Bengal, and P less than it should be for the Arabian Sea. Sorry for this mistake. So Arabian Sea in general, it evaporates more moisture, but it precipitates less. On the other hand, Bay of Bengal evaporates relatively less moisture and precipitation is very high in this case. So these moisture characteristics determine what would be the isotopic compositions of moisture and in turn to the rainfall. I will briefly discuss about the precipitation systematics for those who are not initiated. Now, so we have been collecting samples, rain samples at an island locations in Port Blair here, which is shown here at this dot. So now we have generated about nearly a decade-long record of precipitation isotopic variability, and using this, we are studying the monsoon dynamical processes. And also, I would discuss a little bit about how this can be used to understand the past rainfall variability using the proxies. Now here I like to give a brief discussion about the isotopic fractionation process. So as we know that the water molecule, it has major isotopes like 1H, 1H16O, which is called the major isotopes, the molecule consisting of major isotopes. But there are a small fraction of molecule is there which consist of minor isotope or heavier isotopes. For example, 1H is replaced by 2H or 116O is replaced by 18O. So because of this mass difference, they have some different characteristics, particularly the physical characteristics. For example, when this water evaporates from water body, for example, in the ocean or river or lake, the lighter isotopes, the molecule consisting of the lighter isotopes, they escape faster, as is shown by this cartoon here. Whereas the heavier isotopes, they come later. So as a result, what happens? The remaining water gets isotopically enriched. The remaining water, but the evaporated water, or which forms the clouds, it gets isotopically depleted, which is written here. Moisture is isotopically depleted. However, when condensation takes place, that when this moisture is condensed, the opposite process happens. That is, the condensed water has more amount of enriched isotopes and less amount of lighter isotopes. Similarly, the transpiration process also generates a little different isotopic values. So because of this reason, the isotopic technique is sometimes called the isotopic fingerprinting. That is, by analyzing the isotopic records, one can determine or characterize the source of the moisture. So this is the fundamental issue, and I would mostly describe about these things. Now, how do we define the isotopic values? So it is nothing but the relative difference of the heavier isotope, ratio of the heavier isotope and lighter isotopes of a sample, and of a standard or reference material whose isotopic values are precisely known. So this is again normalized by the 18:16 ratio of the normal of the reference material, and since this number is too small, so we multiplied it by 1000, and this is notation is called per mil. So delta 18O, so I'll be using delta 18O again and again. So that's why I like to give you a definition about this delta 18O. Now, as I said that the moisture, it generally loses heavier isotopes. So as a result, what happens when it rains? Because of the rain out process, it continuously loses the heavier isotopes. So as a result, the isotopic values of rainfall and the rainfall amount, they maintain an inverse correlation, which is called the amount effect. So this figure shows the isotopic values of rainfall as shown by this black line, and the shading, it represents the average value of rainfall and average across the longitude in this case, and in this case average across the latitude. So in either case, what we see here is that negative value means it is the high precipitation events, So what we see here is that high precipitation events, they coincide with the depleted delta 8 values in either case. So this is an example of inverse correlation between the isotopic values of rainfall and the rainfall amount. And this is the basis of the paleo monsoon reconstructions, which I'll be discussing more detail later. Now, this plot also illustrates the inverse correlations between these two parameters in slightly different manner. So this blue line, it represents the TRMM derived rainfall amount over an area, and this red line shows the delta 8 value. So this is the isotopic values of rainfall collected at Port Blair in 2012, and we see there is a clear anti-correlations between these two parameters. However, the correlation is not very strong. It is rather weak, and also it varies from place to place. So here it shows the inverse correlations between these two parameter, rainfall and delta 8 for different years, that is 2012, 13, 14, etc., and at the Port Blair in Andaman Islands. So this relation is rather poor, and so this is a constraint or in reconstructing the rainfall amount. Now, in these slides, I will discuss how we can measure or how we can quantify the past rainfall amount using proxies like speleothems. So so this is in a natural environment when it rains and the rainwater percolates and it goes through the to the cave. What is shown here is that under certain conditions, when certain conditions are made, the stalactites and stalagmites are formed. And what happens? So when this if it is under equilibrium conditions, then delta 18 of speleothem is a function of the two parameters. So one is delta 18 of drip water, which is nothing but the rainwater, and the temperature of the cave. So using this equation, if we have a good calibrations, then using this equation, one can estimate the past rainfall variability. Now, one point is to be noted here is that so this wavy line, it shows the delta 8 variability or atmospheric rainfall, the schematic diagram of delta 8 of meteoric water or rainwater. So this rainwater, when it percolates and when it gets incorporated into the calcium carbonate matrix of speleothem, the isotopic values of rainwater is preserved in the oxygen isotope of calcium carbonate. But what we see here is that the amplitude of the delta 8 variability is actually reduced, and as a result, what happens, the speleothem, it actually filters out the high frequency variability. High frequency means what is happening in weather timescales, and that is the reason the speleothem can be called, it acts as a natural low pass filter. So it will give you the long-term climate variability. Tens of thousands of years, this rainfall analysis has been reconstructed using the isotopic analysis of speleothem from across the globe. Now, this shows the extent of amount effect. Now, in this figure, the bar diagram, it shows the amount effect. Amount effect is nothing but the coefficient of the regression equation between delta 18 and rainfall. This in the red square area, it shows the amount effect for daily samples, and in this case, it shows the monthly samples for different sites in India, which is shown in the right panel. Now, actually, this is the correlation coefficients, and the bottom diagram or the lower panel diagram, it actually shows the amount effect, which is nothing but the extent of depletion of rainfall per 100 millimeter of rain. So what we see here is that in case of monthly sample, these varies from about something about minus 0.5 to a little over minus 2 or minus 2.2. Now, Jadava et al., they have established an equation between delta 18 of rainfall and the rainfall amount. So using these equations, they have reconstructed the paleo monsoon for different regions. However, what we see here, so in this case, they have used an average amount effect of minus 1.5 per mil per 100 millimeter rainfall. That is, for every 100 millimeter rainfall, delta 18 of rainwater is it decreases by about 1.5 per mil. Now, one of the limitations of this using this equation is that this this regression, the coefficient minus 1.5 per mil is not constant. It varies from place to place, as it is shown in this in this figure. And secondly, the correlations between this delta 18 of rainfall and rainfall amount is very poor. So that means it does not capture the entire variability. So there must be other parameters which also control the isotopic values of rainfall. And so it is better to understand what are those factors that control the isotopic values of rainfall. Now, this is one of the speleothem samples that we collected from a cave in Kadapa, and we have analyzed. So these provided the rainfall activity starting from 1400 BC to about 300 AD. So what we see here is that an increasing trend of delta 18, which actually shows the decreasing trend in rainfall, as shown by this arrow. So the so speleothem records actually it's provide because of this reason, that is the amount effect, since it varies widely, so it gives a relative strength of monsoon intensity, and it is rarely used to actually quantify. So now we like to see whether there could be an alternative, things that I will discuss later. Here I will like to give you another examples. For example, Jaglan et al. So they have collected one speleothem samples from Baratan cave in Port Blair, and they have analyzed. So this black line shows the delta variability of their speleothem samples. So they have also compared the delta variability from another sample. This reported in Klang cave, which this is in Thailand. So what they show is that the long-term patterns show very similar variability in these two cases. So now, what we like to examine here is that how we can, if there is an alternative to these rainfall reconstructions of this, that is alternative of the amount effect. Now, as I mentioned earlier, for Bay of Bengal, precipitation is more than evaporations. So the P by E equation, that is P by E is more than 1. So that means that moisture is sourced from other ocean basins like Arabian Sea and Bay of Bengal. Now, Moore et al. They have proposed that convergence of vapor predominantly determines the isotopic composition of precipitations, particularly in cases where rainfall exceeds evaporation. So this is exactly the case in case of Bay of Bengal. So now, so what we like to examine is that whether instead of rainfall, whether any other moisture parameter, how precipitation isotopes respond to moisture parameters. In this case, we have calculated moisture flux convergence, and we see that delta 18 of rainfall shows a much stronger correlation with moisture flux convergence, which is about minus 0.72. So this is on monthly scale. This gives a correlation about minus 0.72, whereas the same delta 18 variability, it shows relatively poorer correlation when we correlate with rainfall, which is minus 0.33. Now, according to Moore et al., the E by P ratio, if we take E by P ratio, then it should show a positive correlation with delta 18. So we have also examined this aspect, and we have found that E by P also shows a strong correlations. The correlation coefficient is 0.67. So in this case, both the hypothesis provided by Moore and et al. Validated in case of Bay of Bengal. So so what we can infer is that precipitation isotopes, it responds better to the moisture parameters than the rainfall amount. Now, there are several parameters, they directly or indirectly control the precipitation isotopic composition. So atmospheric circulation is one of them. In the Indo-Asian region, the monsoon circulation shows distinct seasonality. For example, we get high rainfall. Most of the places we get high rainfall during the summer season, that is June, July, August, September, and low rainfall during the northeast monsoon or October to December. Now, this figure shows the annual precipitation pattern pattern at New Delhi, where it shows the high values during the month of June, July, August, September. This red line shows the delta 18 of this precipitation amount. Now, what we see here is that when precipitation amount is low, for example, in this case, delta 18 stays high. But when delta precipitation amount is high, delta 18 shows low values. For example, this is the low value. So the amount effect is more or less validated. But what we see here is that during the northeast monsoon time, that is October, November, December, rainfall is very small, and but delta 18 increases. But this this is happened. This is true in case of New Delhi and most of the places in India, and in fact in the southeastern region. However, if we see the a small patch in this latitudinal area, latitudinal region of about +5 degree to about +15 degree, this shows the different characteristics. For example, this figure shows the rainfall amount during the annual scale rainfall amount at Port Blair. And what we see here, the delta 18 shows a different characteristics. For example, when rainfall is high, delta 18 also high, and when rainfall is low during the October, November, December, that is not this time, delta 18 goes down. So it shows the different characteristics than rest of India. Now, the reason for such a different characteristics is well known. This is simply because during the summer season, the circulation comes mainly from the Indian Ocean and Arabian Sea, whereas during the northeast monsoon, the circulation it comes mainly from the Bay of Bengal and from the maritime component. Now, isotopically, they have very distinct characteristics. When during the summer season, the moisture generated in Indian Ocean and Arabian Sea, they have high values, and during the winter season, moisture generated in Bay of Bengal, they have relatively low values. So because of these different moisture sources, we get different values, that is high values during the summer season and low values during winter season. This plot shows for example, the April, May, June, July, it shows the positive values. That means the U wind is positive, and but other season like October, November, December, January, the U wind, that is meridional wind component, it is easterly. And so because of these different this seasonal changes in moisture source, so we get different isotopic values, but only for this region. And in South Indian states, for example, Andhra Pradesh, Tamil Nadu, Kerala, Karnataka, and including the Andaman Island and Minaka Island, they get this kind of isotopic behavior. Now, other than the rainfall amount, surface temperature also plays a role in controlling the isotopic values of rainfall. So this plot shows the the linear correlation between surface temperature and precipitation isotopic values at different sites in India, as shown in this map. But what we see here is that the relationship more or less it is very poor. For example, last square value shows about 0.08. In this case, is Sagar in this case is slightly high, but in other cases it is very poor. And in this case, they show opposite behavior. For example, in Kolkata, it is showing positive correlations, and Kakinada is showing positive correlations. So what we see here is that the relation between temperature and surface temperature and delta 18 of rainfall is not coherent. It varies from place to place, and sometimes it changes sign. So we like to examine what is the effect of tropospheric temperature. Now, Xavier et al. They have hypothesized that the circulation, monsoon circulation, it is controlled not by the land ocean temperature gradient, but it is basically controlled by the tropospheric temperature gradient. So they have hypothesized these two boxes. One is southern box and one is northern box. And if we take the temperature difference, average temperature difference of northern box minus southern box, then this temperature difference actually controls the monsoon circulations. And these boxes, the vertical dimension of the boxes is from 600 hectopascal to 200 hectopascals. And this panel, in the right panel, it shows the annual variability of this temperature difference, which is denoted as del TT. This black line, it shows the time series of del TT on an annual time scales. So during the initial months, so del TT is negative, but around June it becomes positive, and this point is called the monsoon onset. That is, when delta T becomes 0 or turns positive, the monsoon onset takes place. And during the monsoon season, this temperature remains positive. And again at the end of monsoon season, again it turns negative. So this point is called monsoon withdrawal. So this area, which is shown here by this gray color, actually this represents the intensity of monsoon. Xavier et al. They have shown that if we take the all India monsoon rainfall and this area, they show a strong correlations. So they propose thermodynamic index, which is called TISM, or thermodynamic index of summer monsoon variability, which they, according to them, is a monsoon index. So this is a thermodynamic index. Now, other than thermodynamic index, there is a circulation index or dynamical index, which is proposed by Webster and Young. So they have taken the meridional wind within these boxes, and then they take the difference between meridional wind at 850 hectopascal and at 200 hectopascal level. So this also provides another index of monsoon variability, so which is shown here by this blue line. So this is the Webster-Young index, and this is the delta T index proposed by Xavier et al. Now, if we calculate, if we examine the covariation between Webster-Young index and delta IT, we see that they show a strong covariation. For example, this is the case for Port Blair in 2016, and this is for 2017, and this is for 2018. So in all cases, they show strong positive correlation. But such kind of correlation is not seen in other cases. For example, this is a Cox's Bazar in Bangladesh, which is also strongly influenced by monsoon rainfall, but the isotopic values of rainfall at Cox's Bazar does not show such kind of covariability. So this kind of characteristics is only seen at the South Peninsular India and the island regions. So what is shown here by this shading. Now, using this, so we call it isotopic seasonality. That is high values or high values, relatively high values during the summer season, and relatively low values during the winter seasons. So we now like to use whether this seasonality we can use to study the monsoon processes. For example, we have shown here how we can estimate the monsoon withdrawal date. Now, if we plot the Webster-Young index along the x-axis and delta 80 or precipitation along the y-axis, then we get this kind of scatter diagram. And by employing k-means cluster analysis, we get the two different clusters. That is, positive values, high values, they stay in this area of this in this two-dimensional space, and the low values, that is both when Webster-Young index low and delta 8 also low, they stay in this point, this area of the this two-dimensional space. So now what we do, we label the points by their respective dates. And so this circle, this red circle, it represents the summer clusters, and the gray circle, it represents the winter clusters. Now we identify the last date in the summer cluster, and we identify the first date in the winter clusters. For example, in this case, the last date in the summer cluster is 22nd October, and the first date in the winter cluster is 23rd October. So what we define is that during this period, that is 22nd October to 23 October, actually monsoon transition has taken place. So this is how we can estimate the monsoon withdrawal date. Now, so we have also used the delta T method to compare our values with the so-called this thermodynamical method of estimation of monsoon withdrawal onset and withdrawal date. So in this case, according to Xavier et al., the withdrawal date is 21st October. But what we have got, it is 22nd October. So what we see here, that isotopic technique provides a very close, it has a very good agreement with that provided by the thermodynamic index of monsoon variability. This is to be noted that at at current conditions, we cannot estimate the monsoon onset date. This is simply because during this time period, that is January, February, March, April, it does not rain a lot. So that is why we do not get sufficient number of samples, and so because of we do not get statistically robust estimation. So that is why we have estimated only the monsoon withdrawal date. So that means, so it also means that precipitation isotopes have some dependency on the tropospheric temperature rather than the surface temperatures. So now here we examine how they behave with the tropospheric temperature. Now, other than the Port Blair, we have also collected samples from two places. One is Minicoy Island and one is Trivandrum. And what we have found is that the delta Itno values of precipitations in the island region, for example, in case of Port Blair and Minicoy, so they show relatively stronger correlations with the tropospheric temperature, whereas the precipitation values at the land region in Trivandrum, they show weak relations at the with the tropospheric temperature. The reason being that the tropospheric temperature, actually delta T, it is defined in such a manner that it does not get affected strongly by the surface temperature. That is why the lower dimension of this box, it has 600 hectopascals. So, but nevertheless, the surface tropospheric temperature and surface temperature, they have certain dependency, and this dependency varies from marine environment to terrestrial environment, and that is simply because the latent heat liberation is very different in these two environments. So as a result, so we get delta Itno of marine region, they have so stronger correlations with the tropospheric temperature is to decouple the effect of circulations and the temperature. So now, after doing these things, what we have found is that the circulation actually plays a very little role in controlling the isotopic values of rainfall. So whatever the covariability as seen in this picture, it actually does not represent a causality. So that is the conclusion of the study. So now TT, actually TT means the tropospheric temperature, actually it predominantly represents like NO and ANO, etc. And when moisture, so it is and not only global parameter, it is also controlled by the local processes, that is global processes as well as local processes. Both these processes are involved in controlling the tropospheric temperature. So as moisture moves up vertically, the local and large scale processes, they get coupled at every grid point. Such kind of moisture characteristics make the precipitation isotopes respond to large scale processes. So it is, so correlation analysis, it shows that the tropospheric temperature gradient actually controls it is not the rainfall or the circulations which controls the seasonal variation of precipitation isotopes. So delta T modulates the isotopic values, then, and now the question is, if delta T modulates the isotopic values, then we could expect a positive correlation between the summer monsoon intensity and seasonal gradient in precipitation isotopic values, which is represented as delta 18O. Now, so we have tested this hypothesis. So we have plotted the thermodynamic index of summer monsoon variability along the x-axis and delta the isotopic seasonality along the y-axis. And what we see here, there is a strong correlation between these two parameters. Now, since TSM basically it represents the monsoon intensity, so we can replace TSM by summer monsoon, the Indian summer monsoon rainfall variability. But in this case, we see the correlation is rather poor, which is only 0.26. But one point, in this case, this point, and this case, this point, they look to be outlier. So if we remove this point, what we see here is that this removal of this point, in first case, the correlation coefficient marginally improves. 0.77 becomes 0.82. But in this case, 0.26 becomes 0.86. So it simply means that delta 18O, that is the difference between the seasonal difference of 18O, it is very sensitive to small change in rainfall. And because of this reason, it is not an ideal candidate to use as rainfall reconstruction. So what we propose here is that instead of the instead of attempting to reconstruct the rainfall, the delta 18 variability can be used to reconstruct the TISM, that is the thermodynamic characteristics of the atmosphere, which in turn could be used to get the rainfall variability. So so this was published. This was and one thing to be emphasized here is that this method is completely independent of amount effect, which varies across the latitude and longitude of the Indian subcontinent. So this paper was published last year, which is shown here. So now I like to discuss about the interseasonal variability of precipitation isotopes. Now, so what is observed is that if we take the isotopic time series at various places in India, for example, this figure shows the isotopic time series on interseasonal time scales, that is June, July, August, September. It always shows a decreasing trend. For example, this is Dhanbad, this is Varanasi, Kanpur, New Delhi, Bhopal, Ahmedabad. So this was published by Mithun et al. 2018, and we have also observed similar results in case of Nagpur. For example, this is 2015, 2016, and 2018 data. So there are so what is the reason for that? So we know that the rainfall actually it does not increase continuously. It shows somewhat a generally it shows high values during the July August, and it symmetrically goes down in early monsoon and late monsoon period. So it does not show any trend. So it simply means that the rainfall amount, it does not control the isotopic values of rainfall on an interseasonal time scales. So in this case we wanted to examine so what could be the other factors that may be controlling the isotopic values of rainfall on an interseasonal time scales. So these we define as LEMPIC. So it means the late monsoon, early monsoon precipitation isotope gradient. For example, if we see in this case, the precipitation value is about minus 4, and in this case is minus 13. So the difference is something about 10 to 11 per mil. So LEMPIC value is 10 to 11 per mil. Sometimes it goes as high as 15 per mil, but it also shows variation across the spatial scale. So this is another paper is published last week. So in this case, so we wanted to examine.
How are you doing?
We wanted to examine how this LEMPIC varies from across the Bay of Bengal. For example, so we analyzed the isotopic values of rainfall at Port Blair, and this is at Borisal, and this is at Darjeeling. And this figure shows the this is the rainfall amount. This blue shading, it represents the rainfall amount, and this red bar, it shows the isotopic values on a monthly timescales. Now they show similar variability in case of Borisal, and this is in case of Darjeeling. So what we see here is that the isotopic value actually the decreasing trend, it actually increases, that the slope actually increases from south to north. For example, this dotted line, it represents the slope that is trend in case of Port Blair, which has a gentle trend, and in case of Borisal, the slope slightly increased, and in case of Darjeeling, it shows the maximum values. So that means the the slope value increases along the northern latitudes. So now what we have done, we have analyzed the so this figure shows the major back trajectory analysis for Port Blair, that is from where the maximum amount of moisture is coming. So for example, most of the moisture comes from the Bay of Bengal, shown by this blue shading, but significant amount of moisture also come from the Arabian Sea as well as from the Indian Ocean. Now this figure shows the delta, the isotopic values of vapor for these three sites: Port Blair, Borisal, and Darjeeling. So this means isotopic values of vapor means it represents the isotopic values of vapor at 900 to about 500 hectopascal level average value. And in all cases, they show a similar trend what we have observed in case of surface precipitation values. Similar kind of observations we have also observed in case of in Port Blair. In 2015, we collected ground level vapor and the rainwater, and what we have seen here, they show similar kind of covariability. So these results shows that the the upstream moisture, the isotopic values of upstream moisture, they actually control the isotopic values of downstream precipitation values across the latitude. Now, Midhun et al., they have analyzed the precipitation isotope at different places, for example, in central India and in East India. And this figure shows that they have, along the back trajectory, they have calculated the total rainfall amount. For example, this is up to about 10 days, that is 240 hours. So what they have observed is that something up to about 4 to 5 days. So this correlation coefficient between isotopic values of rainfall and rainfall amount along the back trajectory, it increases. That is, the negative correlation value increases, and then after that it gets stabilized. So, for example, here they more or less constant. So what they conclude is that the first 4 or 5 days convective rainfall actually control the isotopic values of rainfall. Now, similar analysis has been done in case of these 4 places. So what we observed is that very similar results what we have found in case of Port Blair. So it shows, so now if we saw the shading region, it shows about 4 to 4.5 days. That is, during this time, if we take the rainfall amount and along the back trajectory and do the isotopic and correlate with the isotopic values, so the correlation become maximum, except in case of Darjeeling, which shows slightly different behavior. Similar behavior is shown in case of the Euler with the delta 8 of hydrogen isotopes. For example, within the first 4 days, so if we take the Euler, which represents the convective activities, so we get the maximum correlations, that is about 0.4 to 0.6, and afterwards it decreases. So similarly, if we do with rainfall, not isotope, with rainfall, so it also shows about maximum correlation up to about 4 days, and then it stabilizes. So what it means is that the convective activities, also the modulated by rainfall, so it actually controls the precipitation isotopic values for the first 4 to 5 days. Now, there are other reasons also that also controls. For example, the atmospheric, the vertical motion of the vertical motion, which also controls the isotopic values across the latitude. So now, I like to summarize our studies. So what we see here is that precipitation isotopes better respond to the moisture parameters than the rainfall amount, which may be potentially useful to reconstruct moisture dynamics. Typically correlate with the monsoon circulation, low-level circulations that carries oceanic moistures. However, it does not have much physical role to control the precipitation isotopic values. Tropospheric temperature anomaly plays a significant role in determining precipitation isotopic compositions in southern peninsular India. When plotted against the Western monsoon circulation index, the isotopic records reveal a characteristic seasonality. And such kind of seasonality can estimate, it has the potential to estimate the summer monsoon withdrawal date using the proxy samples. For examples, there are many corals which grow in the Andaman Island region, and the corals generally have a very high growth rate. So across in a year, so if we have sufficiently high resolution, for example, if we can resolve about monthly scale samples or even better than monthly scale samples, then it may be possible to get the monsoon withdrawal date using the corals on a weekly time scales. It cannot give on a daily time scales, but it may be possible to get on a weekly time scales the past monsoon withdrawal dates from the proxy records. The seasonal difference in precipitation isotopic values, it may have potential to study the thermodynamic characteristics of the atmosphere driven by the monsoon systems. And because of these characteristics, this may also be used to reconstruct the past monsoon variability, which is not possible. That is, quantification of monsoon variability is not possible using the amount effect, which is currently practiced, particularly in case of speleothem studies. The isotopic depletion across the summer season is controlled by upstream vapor transport and the rainfall and the convective activities along the moisture trajectories. So this also gives an idea how the atmospheric processes it control the isotopic values of rainfall on a shorter timescales, that is particularly on a interseasonal timescales. But this the mechanism for interseasonal timescales and seasonal timescales and longer timescales, particularly internal timescales, they are quite different. So this also puts a limit of extracting the monsoon information, particularly on a seasonal timescales. So I like to thank my collaborators, and also I also acknowledge the funding agency like IITM and Ministry of Arts Science and IAA. Thank you.
So thank you, Dr. Supriya Chakraborty. It was a very wonderful presentation and very important. I think you have brought out very clearly about how the precipitation isotopes can be basically used for studying the monsoon processes. So the presentation was very good, and you started with the isotopic fractionalization, and thereafter you demonstrated about the inverse correlation between the precipitation as well as the precipitation isotopes, which you termed it as the amount effect. Then you had actually also shown how the inverse seasonal variation of rainfall and the oxygen isotopes for a location, island location that is in Port Blair. Yeah. So I'm just giving an overview, and I'm just there are some couple of questions which I've noted down, and you have finally actually brought out a very good presentation highlighting how the intra-seasonal variation of precipitation isotopes across different locations of India and the role of upstream rainfall along the back trajectories. Now, there are some few questions actually which I have noted down. You have actually mentioned about the inverse seasonal variation of rainfall and the oxygen isotope. How do you find it for the other land-based location, landlocked locations? For example, the northeast part of India.
Yeah, exactly. That is a very good question. But so currently, what practice is followed that delta 18O. So everybody uses the inverse correlations between delta 18O and rainfall. But practically nobody reports the actual amount of rainfall. That is quantification. Practically nobody reports. So this is simply because the amount effect it varies space to space. It does not give a constant value. So that is why. But since the negative correlation it is more or less true for any case, in case of land, in case of ocean, it is more or less true. So you can actually examine what is the trend of monsoon rainfall in the past time scales.
Right. And also in one of your slide, you showed about the amount effect, in which you showed a negative correlation for different locations of North India. And this correlation seems to be very high compared to southern part of India, like Kerala.
Yes, right.
So what could be a probable reason for why it is the differences are high actually?
So these differ. It arises mainly because the local factors which also control the isotopic values of rainfall. For example, if you go to the if you go to northern India, particularly in the hilly regions, so there are topographic effect. So so they incorporate some noise in the isotopic values. So the isotopic values get more noisy, and as a result, so they may not show a good correlation with the rainfall amount.
Okay, I think the final question, actually the last question which I have, it is we are finding actually the climate is changing very fast and global warming is also happening at a very rapid pace. So under these conditions, which is actually going in a very rapid stage, how these precipitation isotopes can play a role actually as a proxy basically in this?
Yes, exactly. That is in fact very good questions. So now I like to give you an example. For example, recently one paper was published by IASC group. So they have done the modeling analysis, and what they have done is that so they have calculated. They have examined the what are the factors that influence the starting with the discussion. What they found out
Okay.
more and more moisture in the atmosphere. So now the question is whether the monsoon is getting influenced by the rising amount of moisture or it is something else. So these people, what they have demonstrated that actually, so during this roughly about 20,000 years ago to 10,000 years ago, the monsoon was influenced more by the rising level of moisture.
Okay.
But during the Holocene, that is 10,000 years ago to modern time scales, so it is not the moisture, but it is basically the cloud feedback mechanism which control more than the monsoon rainfall. So precipitation isotopes can give you, so if you understand well how the precipitation isotopes is controlled, means isotopic values of precipitation is controlled by these different processes, then you can validate these models, and also you can probably make some predictions for the future monsoon.
Yeah, that is very quite interesting, actually, very interesting. Yeah. So thank you, Dr. Supriya. I think there are no more questions, actually. So on behalf of the Ocean Society of India, I thank you for this wonderful talk. And I believe actually that this work actually will be having a lot of importance in the coming year because of this changing climate and the variable type of precipitation that we are having in Indian mainland and the islands. So once again, I thank you very much, Dr. Supriya, for the wonderful talk. Thank you very much.
Thank you, Dr. Prasad Bhaskaran, and particularly OSI for giving me the opportunity to present my work.
Thank you, sir. Thank you.